And welcome back to Calculus 2. In this video, we're going to talk about polar coordinates, a very special case of parametric equations. It's a whole new coordinate system. Technically, you could define any set of parametric equations in terms of more than one variable. We didn't. We generally just did it in terms of t, but it's fine to define them in terms of two more variables, like, say, t and v. And that's kind of what these are doing. Instead of defining a point by an x and y coordinate, x is a horizontal position and y is a vertical position, we're going to set up two parameters that define a point by its distance from the origin, its radius basically, and the angle from the origin. So for example, let's take a very simple point. Let's take the point 1, 1, right? It is 1 unit this way, 1 unit up. 1 unit up, 1 unit right. If you do Pythagorean theorem, this distance has to be square root of 2. The Cartesian point is 1, 1. Well, the polar point would be the radius, square root of 2, and the angle from the natural position of the x-axis, which would be 45-degree angles, or it's always given as in radians, so it would be pi over 4. And it's a novel way of describing a point, because basically you can define every point then with a radius and an angle between 0 and 2 pi, like, this point right here. Say it's at negative 13 and then 17, right? Well, you can find this distance by doing the square root of 13 squared plus 17 squared. And then the angle, well, you can find that by doing some trigonometry, because this side is 17, this side is 13. If you'd say do tangent of 17 over 13 is the angle. Well, is the tangent of theta is 17 over 13 if this is the angle. There we go. So theta would be, well, not quite the inverse tangent of 13. The actual theta would be the inverse tangent of 17 over 13. But the actual angle I'd want from here would actually be pi minus inverse tangent of 17 over 13. Because this would be the inverse tangent of 17 over 13. I'd want this angle, which is 180 degrees, or pi minus this angle. And you could then, calculate those values. But yeah. So this is what we're using in these three sections when we're talking about polar coordinates. And you might think, well, why are we bothering to define a whole new set of coordinates? There's some very nice things about these. They actually make some graphs much easier to manage. Some kinds of functions and equations have much simpler formulas in polar coordinates than Cartesian coordinates. I actually find it a lot harder to graph by hand in polar coordinates. Most people, I just recommend do it in your calculator, but it's important to know how to do it by hand so you can kind of know whether you're doing it right in your calculator or not. But here's some equations relating polar coordinates and Cartesian coordinates. They all come from just basic trigonometry. X is r cosine theta, y is r sine theta. We basically just did this several times. The radius squared is just the sum of squares of the x and y's. And we use this one as well. Tangent theta is y over x. So let's mess around with these in some exercises. So here's an interesting problem. It's asking which polar coordinates label the same point. So if we think about this, we have a pi over 3 angle. Pi over 3 is a 60-degree angle, so it's about like this. And maybe a little bit taller. Yeah, probably more like that. About like that. And this tells you how far out it goes. Now, this would actually be going out of +2. -2 means it goes backwards, so it goes down like this. So we're looking at -2, -2 pi over 3. Well, which polar coordinates are the same point? Well, if you look at this one, that's 2 negative pi over 3. So that's looking at a negative pi over 3 angle. So that's this angle. But it is a positive radius, so it is actually going out this way. So that's 2 pi over 3. And then we just have r theta, so that's very generic. So you can just draw that wherever you want. I will draw it over here. R theta. Alright. Theta plus pi. Theta plus pi, that adds 180 degrees, so that means we're looking at this. That's r theta plus pi. So we haven't had any line up yet. Then, negative r theta. Well, theta takes you out this one, but negative takes you backwards. So this is also negative r theta. So these two are the same. Alright, 2 negative 2 pi over 3. Okay. So negative 2 pi over 3 would be a pi over 3, a pi over 3, and then straight out would also be 2, so 2 negative 2 pi over 3. So these, let's see, this one and this one are length. Negative r theta plus pi. So theta plus pi is this one, but then negative r takes us back out here. This is a negative radius, so negative r theta plus pi. So this one and this one. I maybe should just be collecting these together. So we have A and F, A and F. We have D and E. And we have C and G. Alright, let's see if B and H match up. Haven't had anything go together with this. So 2 pi over 3. So here's pi over 3. But then 2 pi over 3 would be here. But then it's negative, so it's down here. Yeah, so it's negative 2 pi over 3. So yeah, B and H go together. So that's the answer to that. Which polar coordinate pairs label the same points? It's all about just following the rotations around. Negative radii means you go backwards instead of forwards off the angle. Negative angles just mean you rotate clockwise instead of counterclockwise. Alright, find the polar coordinates. Specifically between negative pi to pi and r greater than 0. That's worth pointing out. The biggest problem with the polar coordinates, and I don't really know whether it's a big problem or not, is that every point can be written multiple ways because of multiple rotations or rotating around and hitting a negative radius. It's just one of the... You could call it a pitfall of the coordinate system, but it's also kind of one of the nice things about it. So it's just one of the properties of the system. So down here, we're going to be finding polar coordinates of Cartesian coordinates, but specifically ones that have their angle between negative pi and positive pi, and their radius as a positive number. For example, negative 2, 2. Well, negative 2, negative 2. Well, we want this version, because with this being r equal 2. So we're going to actually have to find the angle that's less than pi. So we're actually going to want this one. So that's a 45-45 triangle. So that's a pi over 4 here. So that would be negative 3 pi over 4 as the angle. And then the radius, well, you just do the math. You know, x squared plus y squared is r squared. So r is the square root of, let's see, 4 plus 4. So that's the square root of 8. So that is 2 root 2. So that's A. B. Remember, this is the r, this is the theta coordinate. 0, 3, huh? So that's 1, 2, 3. That is a 90-degree angle. So that's pi over 2. And then, I mean, you can't get any clearer than that as a radius. That's r equal 3. Don't even need to calculate that. It's right on the axis, going straight up. C. Let's see. The angle is 1. No. These are Cartesian coordinates. My bad. So that's negative square root of 3. So that's like 1 and something. And then 1. So if we do our radius calculation, our radius, let's see, would be negative square root of 3 squared plus 1 squared equals r squared. So that's going to be r squared equals 4. So r equal 2. There's that. Then we need to actually come up with a formula for the angle. So let's see. This side is square root of 3, this side is 1. So tangent of theta equals 1 over square root of 3. That's actually the 30, 60, 90 triangle, isn't it? Yeah, it is. So theta would have to be pi over, let's see, the opposite side is the shortest side, so that's the side opposite the pi over 6, the shortest angle. So pi over 6 is the angle. And it's in this quadrant, so it's actually be pi minus pi over 6. So this angle we want is, I should really use a different thing. I'll call it beta. Beta equal pi over 6. So theta would equal pi minus pi over 6, which is 5 pi over 6. And lastly, 5, negative 12, so 1, 2, 3, 4, 5, you know, way down. I can't really draw it to scale because the stuff I've drawn there, but it's in quadrant 4, so we're going to be doing a negative angle for that. I can tell the hypotenuse of that is going to be 13 because it's a famous triangle, the 5, 12, 13 triangle. But the angles aren't super nice for it. It's just true. So the opposite side is the negative 12. The adjacent side is the 5. So tangent of theta equals negative 12 over 5. So that ought to give us something. Theta is just the inverse tangent of negative 12 over 5. And honestly, I think that's as good as we're going to get as far as exact values. The 5, 12, 13 triangle doesn't have nice multiples of pi. So yeah, if you want to see what it is in radians, it's inverse tangent of 12 over 5, negative 12 over 5. I'll just put the negative down here. Yeah, it's negative 1.176 rounded to really to 4 decimal places, but we'll just leave it as this. So our hypotenuse is 13 though, so our radius is 13 and our angle is inverse tangent of 12 fifths. And there we go. On the next problem we're going to look at, I believe we're going to look at converting an equation between polar and Cartesian coordinates. And just the things to keep in mind, you know, we had our formulas for this. We had x equal r cosine theta, y equal r sine theta, x squared plus y squared equal r squared. And tangent of theta is y over x, opposite over adjacent. Alright, this one's fairly simple to deal with just because we have r cosine theta and r sine theta. This is literally the main diagonal line, y equal x. So that's what the line looks like. R sine theta equal r cosine theta. Really a bit more complicated in this version, in polar coordinates than this version, but it's still not that hard to deal with. This one takes a little bit more work. Certainly, this is y. So that's y. ln r plus ln cosine theta. Converting to Cartesian form. Let's see. Law of logarithms, if you have two logarithms of the same base, you can combine them. So this is ln of r cosine theta. Well, that's not too bad, because now that's y equal ln of x. Yeah, that's not too hard to deal with. Alright, this is Cartesian to polar form. So basically we want to convert everything over to polar form, everything in terms of r's and thetas. I honestly find this way a little bit easier just because we have these, r cosine theta and y equal r sine theta. Because then this is r squared and x squared plus y squared equal r squared. So you can combine those two and you have r squared. Then that's r cosine theta times r sine theta. Then that equals 1. So then just simplify r squared plus r squared sine theta cosine theta equal 1. I think I'd probably go ahead and solve for r squared just for good measure. R squared is going to be 1 over 1 plus sine theta cosine theta. But I don't know, it's kind of 6 of one, half dozen of the other once you get to here. Basically got your answer because you can factor out the r squared. 1 plus. That's how I did this, by the way. I'm sorry if you missed that algebraic step. I factor out the r squared and then divide by the 1 plus sine theta cosine theta. I think I'll leave these up there, but erase this, and we'll move on to the next one. Alright, this is the equation of a circle. So, a circle centered at the origin is probably the easiest polar equation, because like if you want the circle of radius 3 that's just centered at the origin, it's just r equal 3. Because every angle you would pick, the radius would be 3. So, circle centered at the origin is super simple to do in polar equations, polar form. This is a little bit more complicated because it has been shifted. You know, that's 2 units to the right and 5 units up. But we can probably still make it come out. I mean, first off, just plug in, I guess, r cosine theta plus 2 squared plus r sine theta minus 5 squared equals 16. There's some simplification you can do if you multiply this out, so I guess it's worth doing. R squared cosine squared theta plus, it'll be 4r cosine theta plus 4 plus r squared sine squared theta minus 10 r sine theta plus 25 equals 16. So, you know, 4 plus 25 and then subtracted from 16. So it's 29 minus 16 is 13. So that'll be negative 13 on the right. You can combine these two because you can factor out the r squareds. And then sine squared plus cosine squared is 1. So you just get r squared plus 4r cosine theta minus 10r sine theta And then that would be the equation. I don't really know that that's a whole lot better than that. We certainly did some stuff to it. And that's really the end of our intro to polar coordinates. We're by no means done with them. We're going to look at graphs next and then some calculus with them. It's basically the same calculus we just did with parametric equations, since this is still parametric equations. It's just using 2 parameters instead of 1. So, the next we're looking at graphs, which graphs in polar coordinates is also probably going to be a pretty short video. Not because it's super easy, but just because I don't necessarily want you doing a whole lot of it by hand. It is just pretty hard to do by hand. See you in the next video. Have a great day.